Exam one went about as well as an exam could go. That was great. I mean, pretty much everyone did well on it. The only mistakes people made regularly were on number 4. So I'm going to go through number 4 just to make sure. So check along on yours. I mean, there were some things that people did that weren't exactly right, but I sort of gave a little wiggle room and whatever. So just check and make sure that that everything I'm doing makes sense to you. Okay, so exam 1, number 4. This was a particle statics problem. And there was an incline of 30 degrees with the horizontal. And a cart, and then a mass sitting on top of the cart. The cart had a mass of 10 kilograms. The box on top was 5 kilograms. And then there was a 100 Newton force. And a horizontal cable connecting the cart to the incline. And we want to calculate the, the force on the 5 by the 10. I just write that 5, 10. We want to calculate the force applied to the 10 by the cable. So I'll think of that as just the cable tension. And we want to calculate the normal force applied to the 10 kilogram by the incline. Okay, well, let's just do them in order. To calculate the force on the 5 by the 10, we can just isolate the 5. So a free body diagram of the 5 kilogram. There's a weight force of 5 times 9.81, so 49.05. And there's a 100 Newton force that's perpendicular to the surface. And then there's a friction contact applied to the 5 by the 10. So that's F510. The only thing that we're going to have to find an angle for is that 100 Newton force. So if we think of our coordinate system like this, here's the x-axis, y-axis. The angle that's given for the incline is 30 degrees. Okay, so we know that between the negative x-axis and this vector is 30 degrees. And then we know that that's perpendicular to the force we want. Try to make those look perpendicular. Nope. They're dry. Yes. Okay, so these are perpendicular. Well, now from the positive x-axis to get to that first vector, the angle is 180 minus 30, so 150. And then if you go counterclockwise another 90 degrees, so 150 plus 90 is 240. So that 100 Newton force is going to be 100 times cosine and sine of 240. Newton's second law, we have the weight force, 0, negative 49.05. We have the 100 times cosine and sine of 240, which is negative 50, negative 86.6. And then we have the force on the 5 by the 10, x and y components. And the components themselves are not vectors, so those don't need the vector symbols on them. That's everything, so set those equal to 0. And you get that the force on the 5 by the 10, you can do it component by component. You get positive 50 for the x component, and for the y component, you get 135.65. And now once you have that, you have two options for solving the rest of this stuff. You could isolate just the 10 kilogram, just the cart, and use Newton's third law, because you know that the force on the 10 by the 5 is the negative of this. Or you could just isolate the whole thing. Either one works fine. So I'm going to just do a free body diagram of both of them. Okay, so there's the body. We have a normal force. We have a weight force. And those are not perpendicular. I mean, are not parallel or perpendicular. The two together are 15 kilograms, so 15 times 9.81 is 147.15. And then you have the 100 Newton force. And then you have the cable force that's horizontal. And that's everything. So now Newton's second law. Well, again, let me erase this and let's figure out the angles. We already know, we've already expressed the 100 Newton force, so we already have that in vector components. But for the other one, well, maybe one way to do it would be, we know that this one that we already did is at an angle of 240. And that means that the one that's exactly opposite that we haven't done yet, is 240 minus 180. So theta for this is just 60. And Newton's second law says 0, negative 147.15. Plus n times cosine and sine of 60. So that's 0.5n, 0.866n, 866. That's the normal force here. And so I got that from, we already knew this was 240, so the exact opposite is 180 from there, or you can just switch the signs. Either way of thinking about it is fine. And then we have the 100 Newton force that we already used in the other Newton's second law. So that one was negative 50, negative 86.6. And then we add the force magnitude T in the negative x direction. So that's plus negative T0. Set that equal to zeros. And you can use the y equation here. It says 0.866 n is equal to 147.15 plus 86.6, 233.65. And then solve for n. And I think that was like 269. And now you can plug that into the x equation, and you get 0.5 times 269 that we just calculated minus 50 is equal to t. And for t, you get something like 84. And really, technically, if you're asked for a force that's applied to something by another thing, you should give the answer as a vector. This was fine with me for this test. If I really care about expressing it as a vector, I'll ask you specifically for a force vector. But really, what you should do now is take this n and plug it back in here. This is the force vector that's applied to the 10 by the ground. And take this t, plug it in here. That's the force vector that's applied to the 10 by the cable. Any questions about that one?
Since cable is angle between x and y, do we want to like try to find the angle?
There's not really any reason to find it. Since that cable is acting in our negative x direction, you could just treat it as vector components. I mean, I'm sure there are ways to figure out that angle and use it, but I don't think you need to. For the angle that the so if you used a rotated coordinate system, nobody did that, I don't think, did they? I didn't see anyone do that, I don't think. Yeah, you could do it. It might actually make the tiniest little bit less work for you, you know, but for the most part in this class, there's not really much reason to do that because one of the big benefits of doing that is that when you're expressing friction as a coefficient times the normal force, you need to break it up into those components anyways, so you kind of need to do that. Since we don't have coefficients of friction ever, it's not as much of a help to us. But okay, so that's all for that one. Like I said, the test was great. I mean, I feel like everyone's pretty much, we're together right now, you know, ready to move on to the new stuff. That's good. And the bad news is the next test is Tuesday. Hopefully you're going to save this week. Yeah, hopefully. Um, and the topics for exam 2 is everything up through rigid body statics number 8. And so that means that there's no 3D rigid body statics. And the reason that that matters, the reason that I need to talk a little bit more before we can do 3D rigid body statics is you have to treat the joints a little bit differently. And I haven't talked about how to do that. So, any questions about the test? Okay. How about homework questions? Yeah.
For question number 5, I'm finding myself with, I get stuck on.
This is rigid body statics.
Yeah, rigid body statics. I'm getting hung up on like things. I don't know how to explain it, but there's like a piece that's attached to the ground that attaches to a body. It's like a hinge of
Oh, okay.
some sort, or a joint.
Yeah.
I don't know, like.
Okay. Do you have the problem with you? Maybe I can. So yeah,
I'm having problems with like this piece, that component of the problem.
Sure. Let me go. Okay, so number 5, it's this problem or this setup that we've seen before in the vector problems, I think. So you have this body like this, and it's connected to this funny J-shaped thing. And a cable like this. And there's a 400 Newton force here. And then it tells you that the centroid is here. And the origin is the center of mass. The 400 Newton force acts at, well, let's label these points. So I'm going to call this, so this is the origin. I'm going to call this point A, B, and C. The coordinates of the point A are negative 0.5, positive 0.02. The point B is 0.05, negative 0.2. And then the point C is 0.6, 0.4. And we know that this angle is 45 degrees. We want to calculate the reactions, and the body's mass is 20 kilograms. Okay, so the question you're asking is sort of like, so we know that that's a pin joint. And we know that a pin joint applies a force to a body that's an unknown force vector because it restricts translation and it lets it rotate freely. So we know that in some way this joint is going to apply an unknown direction force vector to the body. But I think if I'm understanding right, it's sort of like a little hard to picture sort of where that happens.
Yeah.
Ground that applies that force, or is it up here?
Yeah. Is it 2 two different body diagrams and use
So-
Newton's third law?
You can, yeah, you can do that.
Okay.
I think the way to think of it is like, so any kind of pin joint physically, whether it's like a hinge or it actually is just a pin that goes into the thing. At some point, somewhere there's a little bar that has a little round piece that something else rotates around, right? There's an axis and something rotating around it. And the place where that force is applied is the center of that axis, that little bar. Okay? And so if you're isolating the J-shaped thing, the force, that unknown force vector acts right at the start dot, And if you're isolating the ground, which you wouldn't do, but if the ground was something else, like maybe if this was Star Wars, whoa, what's that? And so then you have to do a free body diagram of the creature. That force would be applied to the creature also at that start dot, at the center of that axis.
This will add one into that one pin.
Yeah, that's right. Yeah, well, so yeah, because that pin itself is the thing that's locked in place. So that's exactly where the motion is restricted, is where that physical pin is.
So when labeling that, we would label it R and then point B, R sub B.
That's a good way to do it. Yeah. Or if these were two bodies, which we're not really doing yet for rigid bodies, but if this was body one and this was body two, you would write that force as F12, the force on body one by body two. Yep. But if it's just a force applied by the ground, since there's never really going to be a time that we're going to want to isolate the ground, then you can just call that R or F or whatever. The subscript notation doesn't help so much then. RB is a good name because you can have other reactions at other places. I think I do always use N or R or F, but yeah.
I was just kind of like a notation question.
Yeah.
So like the number, say instead of 400, that's just like force one.
Yes.
Force one doesn't have a vector sign above it.
Yeah, that's right, because so anything with a known direction where that arrow represents an actual known direction, the thing associated with it is just a number. And so if it's a variable, it's just a regular variable. It's only the things that have components. So like when we do this, we'll represent that as a component, horizontal, and a vertical component. And then we'll put the vector symbol over it to indicate that that variable has two components.
So then if it's I don't know if it's the contact force with the north and the friction, then you have the vector sign above it.
Yes, because you don't know the direction then. Because you could have a lot of friction and not that much normal force, in which case it would be closer to being horizontal, like parallel to the surface. Or you could have not much friction, a lot of normal, in which case it's closer to perpendicular. You don't know the direction. Okay, so I'm going to do yeah. So let's draw a free body diagram. The weight acts at the center of mass. So that's 20 times 9.81. So 196.2. And then go around the boundary, and there's contact with the surroundings here. So that's that force RB. And then the cable applies a force parallel to the cable away from the body. And I'll call that T. And then there's a 400 Newton force this way. So now Newton's second law, we have the weight, 0, negative 196.2. The 400 is in the negative x direction, so negative 400, 0. The cable force, go from the positive x-axis to that vector is just positive 45. So that's cosine and sine of 45 times t. Yep. Yeah. That I just called it B because I called that point B. Okay, so this is 0.7071 t. Question?
I was thinking about making the table.
Oh, this is a rigid body. Yeah, let's make the table. Yeah. No, that's good. That's the way to go. I was approaching it like it was particle. So rho, force, moment. And so we have to choose an about point. Like I said last time, the simplest place to put it, sometimes it simplifies the math a little, it's not a big deal though, is to put it where you have the most unknown components of force. So it would be there. Well, actually, in this case, I'm going to do it differently than that. I'm going to put it at the origin because what's the benefit of putting it at the origin? Well, the benefit is that we already have the coordinates of the place where every other force is applied. And then if your origin is at the about point, the coordinates are the row vectors. You see that? So, yeah, let's put it here. Okay. Okay, so first let's do the weight force. The row vector for that is 0. The force is 0, negative 196.2. Cross product is 0. Next, let's do RB. The row vector for that, because the row vector is the vector from the about point to where the force is applied. So if your about point is the origin, the coordinates are the row vector. Does everyone see that? That's not always the easiest way to do it, but in a problem where you're given coordinates for everything, that often is the easiest way to go. You don't have to recalculate anything about those row vectors. Okay, so B, so that means that the row vector is positive 0.05, negative 0.2. And the force is RBX, RBY. We don't know anything about the direction, so you just put those components right in there. And then the cross product is 0.05 RBY minus negative 0.2 times RBX, so that's plus 0.2 RBX. Yeah, I'm just doing this times this minus this times this. In 2 dimensions, those cross products are pretty easy. It's a little more of a pain in 3D to do it in your head.
Yeah, I was doing it in 3D, but if I did it in output, it would be
That's the Z component. That's right. All I'm writing down are the Z components of those moments. Yep. And what do I still have? The 400. So the row vector for that is negative 0.5, positive 0.02. The force vector is negative 400, 0. And so the cross product is 8. And then the last one is the cable tension. That is at 0.6, 0.4. So that's the row vector. The force is 0.7071 T, 0.7071 T, because that angle is 45 degrees. And so you get 0.6 times this minus 0.4 times that, so that's 0.2 times that, so that is 1 or is it 0.14? 0.1414, right? T. Is that right? Okay, so now everything in the force column goes in Newton's second law. Everything in the moment column goes in the rotational equation. So Newton's second law says 0, negative 196.2 plus RBX, RBY plus negative 400, 0 plus 0.7071 T, 0.7071 T is equal to zeros. Neither of those are just like directly solvable for something right now. So at worst, we're going to end up with a system of 3 equations for 3 variables. But let's write out the moment equation. So we have 0.05 times RBY plus 0.2 times RBX plus 8 plus 0.1414 T is equal to 0. And you could do this by substitution, but why not just later on, we're just going to have to use reduced row echelon form to solve this. So let's just get used to doing this in our calculator. It's sort of nice to just know that when you get to the point that any system of equations you treat the same way, I think, you know. I think a lot of professors are sort of like, don't really like the idea of using calculators to solve everything because they, you know, grew up without such an easy ability to do systems of equations on a calculator or whatever, but I don't really see the point in, yeah, exactly. So, yeah. So there's the 3 equations. The variables, let's go RBX, RBY, T, and then this is the constant. And you have to remember to get the constants alone on the other side of the equation. So the first equation says RBX's we have 1, T's we have 0.7071, constants we have positive 400 when you get it by itself. The second equation, RBYs, we have 1. T's, we have 0.7071. The constant on the other side is positive 196.2. And then the third equation, RBXs, we have 0.2. RBYs, we have 0.05. T's, we have 0.1414. The constant is -8. And does anyone have these answers?
X1, negative 1,555.09.
Okay.
Second one, negative 1,758.89.
Okay.
Third one, 2,764.95.
Okay. Anyone else agree with that? Okay, good. Yeah, that's cool. You know, like, so if you're setting up some kind of machinery, well, it's hard to imagine a machine that would have something like that in it. Maybe a sculpture. But whatever you're setting up, so you know how you want it to be set up, you know what force you're going to have to apply, and we can calculate how strong, you know, what the diameter of cable is you're going to need there to be able to support it. How thick the pin is going to have to be there, not break, that kind of thing. And there's one sanity check you can do on this one. You know that cable tension has to be positive. We know because cable forces, we always know the direction. So if that came out negative, something either went wrong with the calculation or not so much in this class, but in the design. If you did all the steps right and it calculated that cable was going to have to push on the thing, then the way you're setting up this structure isn't going to work.
The coordinates for RD also check out as well. They're both going negative. I mean, is that not?
That doesn't matter because what that's saying is, so our coordinate system's like this.
Right.
Okay. So that's saying that force direction is in the third quadrant. They're both negative.
Right.
Okay. Well, this pin, so that's saying that this thing is trying to move opposite that, and it's fighting it by pulling this way. Okay. But this pin can provide a force in any direction to keep it from moving. There's no direction where this pin would let it move. So those can be anything. Okay. But normal forces, rollers, and cables, those force magnitude, you know, the variable values have to be positive on those. Yeah. Any other homework questions you want to see?
Those R's can be negative only on the slots, though, right?
Yes,
Because you
that's right. The slots can go in either direction. Okay, well, I have a couple of problems here. So I thought we could just I'm going to write it up. You guys can work on it, compare answers to each other, you know, just try to get this stuff straight. After you have some time to work on it, I'll go through it and you can just make sure that it's all working in your mind. Yes?
I just got a quick question before you get.
Yeah.
I was just looking at the handout that you posted online.
Yeah.
And it says there's no calculation for the X bar about a triangle. Not a right triangle. But isn't there one?
Yeah, I don't remember. Let me look real quick.
It's just blank. And I was
So yeah, we
wondering-
haven't done centroids yet, so we'll start
Yeah,
looking
that's
at
fine.
I think the idea is a triangle, you can tip it either way and use that same approach to figure out the component. It's not like you can't find it, you know. Sure. And the way let's talk about that when we get there. But yeah, everything there, you can find everything you need about a centroid.
Yeah, I Googled it and it came up with some equation like take the X coordinates,
Mm-hmm.
ABC point, the
Mhm.
But I don't know if that.
All right, so let's do this one first. So let's say that there's a pin joint connected to the ground, and that supports a beam like this that makes an angle of 30 degrees with the ground. And then at the top, it's in a slot, and that slot is vertical. The length of the beam is 2 meters. And the mass is 2 kilograms. What are the reactions at the two joints? Okay, so yeah, take some time, see if you can calculate that. Talk to each other, as you go, compare answers at different points. And after you have some time to do it, I'll do it. And you can sort of, I think it's a good way to see if there are any places where like, oh, I misunderstood this. I should have done this, that kind of, and get to another one. So let's start with a free body diagram. You have to always do a free body diagram for any time you're going to use Newton's laws. So there's a weight force that acts at the center of mass. That's 2 times 9.81, so 19.62. And then the two places where the surroundings make contact with the boundary, one is here. That's a pin joint, so I'll call that RA, that's an unknown vector. And then the other one is up here. And what matters there for the direction of a pin and slot joint is the angle of the slot. That force is always perpendicular to the slot. So you can draw it one of two ways, either to the right or to the left. And whichever one you choose, the sign is going to come out basically to tell you whether you were right or wrong. It'll correct it, So I'm going to draw it like this, but I'll explain how, what you would get if you drew it the other way. So I'll call this RB, and that's just a scalar because you know the direction. Yep.
Is it wrong if you're at another?
To the left? No. I'll show you how it gives you the same answer in the end. Okay, so write out the table, rho, force, moment. And we have to choose an about point. And like I said before, I tend to choose the one with the most unknown forces. So, okay, I'm going to start with RA. I can tell from what, yeah. Because as long as you do it where there's a force, one of your row vectors is going to be 0, so I can see it's there, Yeah. Okay, so row vector for RA is 0. The force is RAX, RAY. Cross product is 0. And then the weight force. Okay, so to get from the about point to the you're gonna go 1 meter, half of the whole length in a direction 30 degrees from the positive x-axis. So that's 1 times cosine and sine of 30. So that's 0.866.5. And the weight force is 0, negative 1962. And the cross product, what do you get for 0.866 times negative 19.62? Negative 16.99? Okay, great. And then the last one is that force RB. That's 2 times cosine and sine of 30. So that's 1.7321. And the force vector, the way I have it defined, that's positive RB 0. It would be negative RB 0 if you drew it the other way. And the cross product is negative RB. It doesn't matter, right? Either one is fine. So now Newton's second law says RAX, RAY plus 0, negative 19.62 plus RB 0 is equal to zeros. You could calculate, RAY we can see is positive 19.62 right now. And then the moment equation says negative 16.99 minus RB is equal to 0. So we know that RB is equal to negative 16.99. And then we can calculate RA. The Y is positive 19.62. And the X is positive 16.99. Okay, so what does that mean about, what does this negative mean on the 16.99? Yeah, so what that means is if you want to calculate this vector, so what's the force vector that this applies to the body? You take that value, negative 16.99, and plug it back into this vector. Okay, and the vector you get is negative 16.990. Okay, that's the vector. If you had chosen what turns out to be the right way from the start, and you have RB pointing that way, okay, that's the negative x direction. So in this point here, in this table, this would be negative RB0. You go through your calculation, find out that your RB value was positive 16.99. And then when you plug positive 16.99 back into your negative RB0, you get the same vector that I have. Okay, so it works out fine either way. Any questions about that one? Okay, let me give you another one with a little bit of a funkier angle. Okay, so let's say that there's a hinge connected to the wall. And it's this beam that has a length of 0.4 meters. And the beam makes an angle of 40 degrees with the horizontal. And then this end is in contact with an incline that's at an angle of 10 degrees with the horizontal. Oh, and then one more thing, at the center, let's say that there's a clockwise couple of 50 Newton meters. That could be applied by two different forces or by a torsion spring. There's a few ways that could happen.
In 2D, are we always gonna be based that couple on the, if it's given or if it's, weld?
Yeah,
Okay.
that's right. Okay, so see if you can calculate those reactions. And this is a frictionless joint. No friction. By the way, if it didn't say no friction here, in order to do this as a statics problem, you would need to treat it like there was no friction anyways. Do you know why that is? Well, really, it's just a matter of adding up the variables. You know you're going to get two variables here, because that's an unknown force. If this had friction, that would be two variables here. So 4 total variables. You know, for a single rigid body in 2D, we only get 3 useful equations. And so we wouldn't be able to do this without more information. Yep. Oh yeah, the mass is 10. Close. Yeah. Okay, so yeah, see if you can.
On the test, remember that. Thanks, Chase. Actually,
Oh man, you got to throw that whole binder out now. Here. So I want to make sure I get the free body diagram and then show the angles on the forces. So free body diagram. There's the body. We have a weight at the center. And that's 10 times 9.81, so 98.1. And then we have the couple of 50. And we have the unknown force vector from the pin. So I'll call that RA, I guess. Doesn't matter what you call it. And then over here, we have a force that's perpendicular to that incline. So if that's the incline, it has to be this way. I'll call that N. And for the table, I'm going to put the about point there. So RA, the row vector is 0. The force vector is RAX, RAY, and the moment is 0. And then the weight force, so our row vector goes from that point at the top left to the center. The angle that we have to use there is -40. So It's 0.2 times cosine and sine of negative 40, which is 0.1532. Yes. Yeah. Oh, yeah, right. And then the second one is 0.1286. And the force vector is 0. What? Negative 40.
Okay.
Oh, yes, so this should be negative, yeah. Thank you. And then the weight is 0, negative 98.1. What do you get when you multiply those? Point 1532 times 98.1, about 15. What? Yeah, about 15. Okay. And then the 50, that's a couple. So we're not going to have either of these. And then we'll have positive 50 for the couple. And then the last one, this normal force is the trickiest angle of this. So yeah. Yeah, so the way to think of that angle to me is draw the coordinate system. And what you're given is it's 10 degrees from the horizontal to a vector in this direction. So that's 10. And then the vector we want is 90 degrees from that. So this one has a theta of 10. This one has a theta of 10 plus 90, so 100. And so this normal force, the row vector is twice this one, so 0.3064, negative 0.2572. And the force vector is n times cosine and sine of 100, which is negative 0.174. And then positive 0.985, if I'm thinking of the right angle. And then take the cross product of that, you'll get something that only has n's in it, you know. So you'll get just some number of n's. Any questions about that? Yeah. Yeah. Yeah, that's from A to the halfway point. Okay. Yep. Because all those row vectors are from the about point, which is A, to where the force is applied. Okay. Yeah. Any other questions? Okay. Have a good weekend. See you Tuesday.